Question 14c. The diagram shows the two curves y equals sine x and y equals sine x minus alpha plus k, where alpha is greater than 0 and less than pi, and k is greater than 0. The two curves have a common tangent at x0, where x0 is greater than 0 and less than pi over 2. Part 1. Explain why cos of x0 is equal to cos of x0 minus alpha. At x equals x0, the curves y equals sine x and y equals sine x minus alpha plus k share a common tangent. So this means two things. Firstly, sine x equals sine x minus alpha plus k, and also their derivatives are also equal. So the derivative of sine x is equal to the derivative of sine x minus alpha plus k. Differentiating both sides with respect to x, we get cos x is equal to cos x minus alpha. Now at the point where x equals x0, this means that cos of x0 is equal to cos of x0 minus alpha as required. Part 2. Show that sine of x0 is equal to negative sine of x0 minus alpha. From part 1, cos x0 equals cos x0 minus alpha. Squaring both sides of the equation, we have cos squared x0 equals cos squared x0 minus alpha. Now applying a Pythagorean identity to express cos squared in terms of sine squared, we have 1 minus sine squared x0 equals 1 minus sine squared x0 minus alpha. Subtracting 1 from both sides of the equation and multiplying both sides by negative 1, we have sine squared x0 equals sine squared x0 minus alpha. Taking the square root of both sides, we have sine x0 equals plus or minus sine x0 minus alpha. Next, we need to determine whether sine x0 equals positive sine x0 minus alpha or negative sine x0 minus alpha. But we're asked to show that sine x0 equals negative sine x0 minus alpha. Now sine x0 equals sine x0 minus alpha plus k, since both curves share a common tangent at x equals x0, and we know that k is greater than 0. This means that sine x0 cannot equal positive sine x0 minus alpha, so the only other alternative is sine x0 equals negative sine x0 minus alpha as required. Part 3. Hence or otherwise, find k in terms of alpha. From part 2, sine x0 equals negative sine x0 minus alpha. Multiplying both sides of this equation by negative 1, we get negative sine x0 equals sine x0 minus alpha. We'll call that equation number 1. Now we also know that sine x0 equals sine x0 minus alpha plus k, since that is the point where the two curves intersect. So from equation number 1, we can rewrite this equation as sine x0 equals negative sine x0 plus k. So what I've done is I've replaced sine x0 minus alpha with negative sine x0 from equation number 1. Adding sine x0 to both sides of this equation, we get 2 sine x0 equals k. Dividing both sides by 2, we get sine x0 is equal to k over 2. And we call this equation number 2. Also from equation number 1, negative sine x0 equals sine x0 minus alpha, and sine is an odd function, which means negative sine x0 can be written as sine negative x0. So sine negative x0 is equal to sine x0 minus alpha. Taking the inverse sine of both sides, we get negative x0 is equal to x0 minus alpha. Now we can express alpha in terms of x0. So alpha is equal to 2x0, hence x0 is equal to alpha over 2. Now from equation number 2, sine x0 equals k over 2, but x0 can be expressed in terms of alpha, so sine alpha over 2 equals k over 2. And multiplying both sides by 2, we get k is equal to 2 sine alpha over 2.